Looking at section 7.4 today, and this one is all about separable differential equations. And let's just get right into it. We are going to cut this a little short and only do the separable differential equation part of section 7.4. The quick review says rewrite the equation in exponential form or logarithmic form. So let's just go back over how to do that. So I know, whoops, that's not quite the place it is. I know that there is an e for the base in a natural log. So I could write this as e to the b equals a. E to the b equals a. That's taking it from logarithmic form back to exponential form. For c, writing it in log form, let's do ln since it's a base of e, and the power is c, and it is the natural log of d. So natural log d equals c. Solving number 2a, I would write it in exponential form first. E to the third equals x plus 2. And then I would solve by saying x equals e to the third minus 2. Divide by 2 on b, and we'd have e to the x equals 5. Now to solve that, let's introduce an ln to each side. Power rule allows us to bring the x down in front, and I get x equals natural log 5 because natural log of e is 1. Here we'd have y plus 1 equals e to the 2x minus 3. And I want to be able to get x out of that exponent position, so I would natural log both sides. That'll make that 1, and the power can come down. So I'd have 2x minus 3 equals natural log of y plus 1. Add 3, divide by 2, and we should be golden. So add 3, divide by 2. I'm just going to say it's a 1/2 natural log. Oops, everything needs to be included in this so that it gets multiplied by 1/2. Quick review on logs, natural logs, that sort of stuff. Differential equations of the form dy dx equals f of y, g of x. Notice this is a function in terms of y, this is a function in terms of x, is called a separable differential equation. We can separate the variables by writing it in the form 1 over f of y times dy equals gx times dx. And then the solution will be found by integrating both sides. So let's give it a try. Here are kind of the steps you'll want to follow. Separate your variables, take the antiderivative of both sides, use the initial condition if one is given to find your c value, and then sometimes you have to describe your domain. All right, so if I start out with dy dx equals, I'm going to distribute that squaring. And by doing that, I can divide by a y squared. So I'm going to bring the y squared to the other side. It would have been division 1 over y squared, which would be a y to the negative 2 times dy, and then I'd have x squared dx. We have achieved the separation. That's usually awarded 1 point on your AP exam. Next, we'll want to antiderivative both sides. So show your antiderivative step. And now it's simply what? Add a power, divide by the power. So I have y to the negative 2 divided by negative 2 equals x to the third over 3 plus some c. And now last step is I just need to solve. Oh, I didn't even catch that. We do have an initial condition. So 0, 3 is our initial condition. I think I'm going to do one more step before I solve for that. So I'm going to have 1 over y squared equals, I'm going to multiply both sides by negative 2. So I'll have negative 2/3 x cubed plus I'll have some new c value there. I could call it c sub 1 if I wanted to. Now let's plug in our initial condition. And it looks like then C is equal to 1/9. And I'm going to go back to the form that it was just before finding C. 1 over y squared equals negative 2/3 x to the third plus 1/9. Now solve for, I gotta fly. Now solve for y. That does not look like much fun, does it? You know what I might do here is take and make a like denominator. So I would want my denominator to be 9 here. I'm going to multiply by 3 over 3 to get me negative 6x cubed plus 1 over common denominator 9. That allows me to take and rotate this fraction so that I can bring y squared to the top, 9 to the top over 1 minus 6x cubed. Then I want to go y equals plus or minus square root 9 over 1 minus 6x cubed. And do I want the positive or negative solution? Well, that really depends on my initial condition. And in here I had a positive y value of 3. So indeed, I do want to just keep the positive case for my solution equation. What do we got here? Solve for y. The equation passes through the point 0, 0, so we should be able to get our c value. And I notice just inspecting this that I'm getting e raised to the y plus sine x. That has an intermix going on. So in order to be able to separate those variables, I've got to be able to write them separately. So do you recall that e to the a plus e to the b, oh, it's not plus, lied, times e to the b equals e to the a plus b. So now if I'm starting with an a plus b, I can swing it back into individual bases. So I'm going to call this e to the y times e to the sine of x. And that allows us to get those two variables separated right there. Now let's keep the things with x on the right and then move e to the y over to the other side. That would be 1 over e to the y dy, or e to the negative y if you wish, equals cosine x sine x, multiply both sides by dx. Let's talk about doing the integral. And oh, no wonder why this looks funny. I'm like, how am I going to solve that? E to the sine makes a little bit of difference. All right. I can solve on the left e to the negative y. It is itself, and then I would have to correct for the negative. That's kind of that chain rule idea. You could set up a u sub and see that coming about. There's that negative dy, so we'd have the negative du equals positive dy. So I know my integral is going to be a negative e to the negative y. On the right, another little u sub, let u equal sine x. Can you see how this works out beautifully? We get a cosine x dx as the du. So this will become e to the u du. That's pretty easy. So e to the u would be e to the sine x plus c. So not very pretty, but I guess that's neither here nor there. Let's find c by plugging in the initial condition 0, 0. That's going to give me negative e to the 0 equals e sine of 0 plus c. E to the 0 is 1. I'm going to get negative 1 on the left. Sine of 0 is 0, so I get 1 on the right plus c. C comes in at negative 2. I need some space. Then we are going to keep, we've got our C value. I'm going to come back to that equation that had my C. So I'm going to have negative 1. No, let's go negative e to the negative y equals e sine of x minus 2. Now, in order to solve for y, I need to be able to bring the y variable down. Let's multiply both sides by a negative. Just keep cleaning it up a little bit at a time. That'll make a positive 2 and a negative e to the sine x. Now let's natural log e to the negative y equals natural log of 2 minus e sine x. That'll make this a negative y equals natural log of 2 minus e sine x. And then bring the negative over. I'll have negative natural log e minus 2, whoops, e and I wrote a 2, e sine of x. And at 0, 0, this should be raised up, shouldn't it? That looks a little funny. I'm like, that wasn't e times sine x. It's e raised to sine x. So just make sure. You probably wrote it right. It was me. All right. Let's go to C, and I think that's the last one we're going to do. Oh, no, I'm going to solve that other one on the backside. All right, so C, coming from problem 10, probably out of the textbook. What would be the difference if I had, instead of this on my left side, instead I had y prime? Would you still do just a separation of variables? Yeah, you would, because y prime means dy dx. So I still am going to work on separating variables. I'm going to have 1 over square root y equals, dy equals 4 natural log x over x dx. And then we want to integrate both sides. So I want the integral of y to the negative 1/2 dy equals 4 integral natural log x over x dx. Okay. Integrating on the left isn't too bad. That would be a y to the positive 1/2 divided by 1/2 is like multiplying by 2. And then I'll have a 4. Allow u to equal natural log x, then du is 1 over x dx. And you'll notice that you have natural log x dx right there, 1 over x dx. So if I make that my substitution, I'd have I'd have u du, wouldn't I? So let's keep integrating. We have 2 y raised to the 1/2 equals 4 u squared divided by 2 plus some constant. Multiply both sides by 2. I think I would. That's going to give me 4 natural log x plus c, some new c sub 1. And let's use our ordered pair. We have e comma 1 to help find c. So 1 goes in. I have square root of 1 is 1. 4 natural log of e, that's going to be a 1 plus c. It gives me 1 equals 4 plus c. So c turns out to be negative 3. And now I just need to go back to there where we were right before we found C, and let's rewrite it. So I would have y to the 1/2 equals 4 times natural log of x minus 3. I'm going to close that off so I can tell that 3 is outside of the natural log. Essentially, we got to square both sides. Y equals 4 natural log x minus 3 quantity squared. And there would be a middle term on there. I just see I have something different. Why is that? Did I make a mistake somewhere? The 4 in the x, let this be u. That's 1 over x dx. So u gets raised to the 2. This becomes a 2. Oh, right here. 4 over 2 is 2, and then I need to divide by 2. This should be a 1. Woo. That should be a 1. E to the first is 1 times 1, and C turns out to be 0 in this case. Okay, then this is zeroed out, and this will get squared. I even forgot that, didn't I? Wow, I really should just start this whole problem all over again, but I won't. We would have had 4 natural log x quantity squared, and then solving y to the 1/2, we have to square both sides. So I should end up with y equals 4 natural log x all raised to the 4th, because I just picked up that when I integrated, I made a squared, and I think I forgot to write that square down as well. So there is the right answer. All right, the last thing is the law of exponential change. If y changes at a rate proportional to the amount present, that is, if it has a rate of change that is proportional to the amount present, we're going to have a k value that represents the constant of proportionality in here. When k is greater than 0, we know we're in constant growth. If k is less than 0, we have decay going on. So it's suggesting that that differential equation, dy dt equals ky, turns out to equal y equals y naught e to the kt. We want to prove that. So let's see if we can do separable differential equations on this. So first thing I'm going to do is bring 1 over y dy on the left side, and I'll leave the k multiplied by the dt on the right side. I want to integrate each side. Oops, get an integral. K dt. And the integral on the left is going to be absolute value y, natural log absolute value y, equals k times t, because we are integrating dt, plus c. K is just some constant. And next, let's e both sides. And that gives me absolute value y equals e to the kt e to the c. If the powers were added, then the bases were the same. And that's going to give me one big C e to the kt. Because e to the c is just some new constant. Typically, they make it a larger capital one for this particular setup. And that is our y naught that we see up there in that law of exponential change. So that's kind of where the PERT formula comes from. The rate of change is greater when y is larger. So if I have more quantity present, the rate of change is larger. And as the amount present becomes less and less, well, then the rate of change becomes less and less. And it decays slower, or it populates less quickly if that y value is small. The compounding continuously on interest is something you have done before. It is not typically ever shown up on a BC test, so I think we're going to stop and not do that. So that will take, I think, 15. Oh, I was going to make WebAssign for you anyway. So we'll scratch this homework and go with a WebAssign. Good day.